Hi, and welcome back to another LeetCode problem. Today we're dealing with 2221 find triangular sum in an array. Excuse me. And as usual, we're going to approach it interview style, meaning we're first going to understand the problem, then check the constraints, go through an example, and then try to come up with a solution and a runtime and space complexity analysis before we write the first line of code. And then we'll walk through the code and explaining it, etc., and hopefully our solution gets accepted by the LeetCode gods. Right, so let's get into it. We are given a zero-indexed integer array nums, where nums I is a digit between 0 and 9 inclusive. Okay. The triangular sum of nums is the value of the only element present in nums after the following process terminates. Let num comprise of n elements if n equals 1. End the process, otherwise create a new zero-index integer array, new nums of length n minus 1. For each index I where I is between 0 and n minus 1 inclusive, assign the value of nums I as the sum of its predecessors modulo 10, where percentage denotes the modulo operator. Replace the array nums with new nums. Repeat the entire process starting from step 1. And finally return the triangular sum of nums. Constraints, well, we already know that the values in the array are between 0 and 9. And there's also a constraint on the length of the array, but what is most interesting to us is that there's at least one element in the array. Cool, so we don't have to deal with an edge case where the array is empty. And for runtime and space complex, we're just going to ignore the fact that there's an upper bound on the length of the array. Otherwise, everything would be constant space and constant time. Okay, example 1. So I guess, so this would be, the top row would be the numbers that we're given, yes. And then we follow the process where we add the two predecessors and take it modulo 10. So 1 plus 2 is 3, checks out. Same for the others. And then as we go down, 3 plus 5 is 8, 5 plus 7, that's 12, but it's modulo 10, so that becomes a 2. All right, I think we understand. And then return the final value once our array reaches size 1. Cool. Here's another example, and this is where the array contains only one element, and we don't have to do anything. We're already done there as well. Okay, so, well, first observation is this kind of reminds me a little bit of Pascal's triangle, right? Where like an inverted Pascal's triangle, where the sum of the child of the next element is sum of the two above it. That's what this kind of reminds me of. Yeah, well, I guess what we could do is we could just implement the first obvious solution, which is just following this recipe that we're giving here. And if we did that, we would have an O of n, well, we have O of n elements to go through in each level, even though it becomes smaller and smaller. And we have n levels, right? So that would be an O of n squared time and an O of n space solution, because we only need to keep track of the current row to compute the next row. And after that, we can forget the current row, right? So yeah, I would say let's just implement this just to shell out a quick solution. In an interview, that's always a good idea to do that. Ask the interviewer if if he's okay with or she's okay with you implementing it, and that gives you some easy points quickly, and you get some momentum. Whereas if you would try now to figure out, okay, how does it with Pascal's triangle work and all that, you could get lost in details, and then time is up, and you didn't produce anything. So go for quick wins. Right. So we're going to say O of n times n time and O of n space. That's going to be our complexity. And we're just going to iterate. Well, we're going to have a while loop while nums, while length nums is larger than 1. And then we're going to do stuff. And in the end, we're just going to return the first and only element in nums that is left. Now to compute the next row, we probably need like a temporary array. And then we will, in the end, after we computed that, we'll just say nums equals tmp. Right, so we're switching out the nums array. And yeah, so now we need to iterate over the elements exactly as shown here. So we just even have the constraints for our for loop given to us here. Isn't that nice? So for I in range 0 to the length of nums, and because that changes, right? So we can't just put n in here, range of nums. We're going to compute the next value. So we're going to append that next value to tmp, and that value is nums at position I plus nums at position I plus 1. But we also need to do the modulo thing, mod 10. Right, and that is pretty much it. If we wanted to, we could just name this new nums. Right, then we're even more aligned with the prescribed algorithm from the problem statement. And I think that should be it. So let's just run it through the test cases. Boom. So that worked. Submit it to see if it really passes all of the tests. Oh, nice. Okay, cool. September. Consistency is key. I'm going to save this. Maybe I should print this out and hang it in my my bedroom. Anyway, so yeah, so that is the quick and easy solution. And now the interviewer would ask you, is there some way we could optimize this? And since I don't remember how exactly Pascal's triangle works, well, what I would do here is I would maybe just look if I can see any pattern here. Well, actually, how does it work? In Pascal's triangle, we have something like, well, we have 1, 1, 1, and so the triangle kind of grows, right? So 1, 4, 4, 6, 1. And in our case, our triangle doesn't grow, it kind of shrinks. But that is equivalent to just chopping off the start and the end from each row in Pascal's triangle and having multiple starting points, right? So if we were to take, let's take this example. So we would have, let's just give the letters these numbers. So we have A, B, C, D, E, right? 5 digits. And then we compute. So in the next row, we have AB, which means not A times B, but A plus B. I'm just using an easier notation. We have B plus C, we have C plus D, and we have D plus E, right? So in the first row, we have 1, 1, 1, 1. 1 times A, 1 times B, etc. In the second row, we have 1 times A, 2 times B, 2 times C, 2 times D, and 1 times E. Okay, what comes in the next row? So we have AB, BC, and then we combine BC and CD. So B, C, C, D. Remember, these are, well, we're adding, right? We're adding, we're not multiplying. And the third one is CD, DE, right? Okay, so how many A's do we now have? Sorry. I think I made a, yeah, how many A's do we now have? Well, only one A, and we also only have one E at the very end. So that stays symmetrical. How many B's do we have? Well, 2, 3. So we now have 3 B's. 3 B's. How many D's do we have? 1, 2, no, wait. Sorry, C, we're at C. 1 C, 2, 3 C, 4 C's. So 4 C's, and then I guess D would have to be 3 again. Yeah, and it's exactly 3 and 1 E. So it's still symmetrical. And we see the same pattern that we see in Pascal's triangle with the addition. Like the 4 is the sum of its two, I guess those two. No, wait, of those two. 3 is the sum of those two, etc., etc., etc. So let's just compute the final step. So that would be A, B, 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 C, 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 D. And the other one is B, C, 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 D, 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 E. So we would, how many A's would we have? We would still have one A, 3 B's here, 1 B here. So that's 4. And now C's, 3 and 3. So that's 6 C's. Interesting. So it's not actually using this sum, it's using this and that to add them. And then we have 4 D's and 1 E. Yes, and that's basically the final result. So the result would then be, well, A, like the result that we need to return would be A plus 4B plus etc. etc. And then of course mod 10. So that would be the final result. So if I now knew the formula for how to compute a value in the Pascal's triangle, it's something, what was that? Wasn't that like n over k or something? N over k, that's how you say it. And you put that into big brackets. That is something like n factorial divided by what was k factorial, and then the difference between the two. And n is always larger than k. So yeah, so that must be n minus k factorial, something like that. But I'm not sharp enough and I don't remember well enough well, which position that exactly calculates. So that would, well, wait. So that would be, I think k is the row and n is the column, if I'm not mistaken. And the way I'm deriving is that if n is always larger than k, that means, you know, n is the x-axis. Because if we're in row 3, how many elements do we have? Well, I think, yeah, no, actually the max value of n and k is the same. I'm not quite sure if that is actually correct, but well, if you want, you can look that up and then figure out how you can calculate that in linear time. Because if you're able to compute that, those values, you should be able to compute, you know, all of these coefficients for all our variables in O of n time. O of n time and O of what space? O of 1 space, really. Because as soon as you have the coefficient, you just multiply it and add it to your result. I'm just wondering, I want to do one more investigation. So Pascal's triangle is 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And then we have exactly this. Yeah, so I guess all we need to do, if we had a function that was n over k, n k, and that computes this thing, and we have to do this in an intelligent way as well, because these numbers can get quite large because we're dealing with factorials here. So we would have to come up with a way of how we could make this simple. And there's probably a whole bag of techniques on how to do that efficiently. Otherwise, you'd have to iterate over, you know, however large n is. And that would, of course, also be very slow in terms of runtime complexity. And then all you do is, if n is your length of your nums array, then you just do for I in range n. You compute the coefficient n over k, and we put in I, and the maybe, so I don't know if that's the, well, it should probably be the length of nums as well. So the last row, if we have, so 0, 1, 2, 3, 4. So maybe it's n minus 1. So that's another thing to consider. Maybe there's an off by 1 error in here. So as you can see, even if this solution is better, it gives you more opportunities to make mistakes. So that's why you don't want to implement this on as your first shot. And then you just have your result. And all you do is result equals result plus coefficient times nums at position I. That is your A, B, C, D, E, etc. And just do modulo 10, then return a result. So that's an outline of a solution that maybe somebody smarter than me can implement. But I wouldn't be able to do this in an interview without having practiced this particular one and seeing how the solution works. So yeah, anyways, so that's the daily LeetCode problem. Have fun with that one. And yeah, see you in the next video.